All right. So, this is a recording for the week 19 session that we missed because of my travels. So, I decided to finally upload it again. Right. So, let's see. We are going to discuss hydrology. So, we'll have three questions. First is going to be based on Muskingum method theory. Second is just going to be match the followings, which formula, which sensor is going used to measure. Maybe I should have written here formula also, right? Which is used to measure which quantity. Then we will have a simple question based on the phi index. Okay, let's start. Question number one. GATE 2014 set 2 question number 20. The Muskingum model of routing a flood through a stream reach is expressed as Q2 is equal to K naught I2 plus K1 I1 plus K2 Q1. Now you might also see this K as C naught, C1, C2. You don't get confused. These are the same things as you remember. Where K naught, K1 and K2 are the routing coefficients for concerned reach I1 and I2 are the inflow to the reach and O1 and O2 or Q1 and Q2 are the outflows from the reach corresponding to the time step 1 and 2 respectively. The sum of K0, K1, K2 of the model is. This is a very simple question. So if you remember from the derivation of Muskingum method, basically how we derived this equation Q2 is equal to K0 I2 plus K1 I1 plus K2 Q1. We use two type of equations. First is that storage in a reach or a channel is a function of both the inflow and the outflow, right? So that equation was S is equal to K into Xi plus 1 minus X into Q, right? And then this is when we used to say that it is a natural current, a natural channel, right? But in general, how we used to say S is equal to K x I power m plus 1 minus x q power m. Right? This was the more general kind of equation, and m is equal to 1 for natural channel. So we used this equation, and then we use this equation in conjunction with ds by dt is equal to I1 plus I2 by 2 minus Q1 plus Q2 by 2. Right, so we use these two kind of equations and we did some arithmetic manipulation to get to this final uh, equation. So I'm not going to go through the derivation. If you feel that you forgot the derivation or if you feel that derivation is important, then you can go through it. But basically, the sum of C0 plus C2, C1 plus C2 is always 1. It's arithmetically not possible to get any other sum other than this. But what condition people often forget is that to use this channel routing, you must get C0, C1, C2 greater than 0. But there will be some cases where you will, so basically you use, you calculate the C0, C1, C2 as a function of x, k and delta t, right? But there are some cases when C0, C1 or C2, either one of these things might come less than 0, right? In that case, what is the standard procedure? The standard procedure is to divide the reach into two reaches and perform the routing once for this portion and then for this portion. So basically, let me clarify what I mean by this. You don't need this for your gate purpose, but just for completeness of this theory, I am going to tell, because this question doesn't have much of the weightage on its own if you don't know the background. So when you write S is equal to kxi plus 1 minus x into q, k has the unit of time, right? And x is unitless. But k represents the time a flood wave takes to travel the channel. And x is in some way associated with the wedge storage of channel. Not directly, but in some way it is associated with the wedge storage. So basically, when you have a river channel, you know that the flow depth is not uniform, right? It changes from where you from the inlet to the outlet. So it might be more at the inlet and then less at the outlet. So this slope or this wedge that is formed because of this non-uniform depth is known as the is associated with the x in that equation. All right. So now, when you have your either of the coefficients of Muskingum method C1, C2, C3 less than 0, and what do we mean by dividing the reach into two is that you divide your k, which basically is associated with the length of the reach through time, because k represents the time a flood wave takes to traverse the channel. So you divide the k into two and then you perform this routing. So you know I1, I2, I3 till all the i's, all the inflows at this inflow. You know the initial Q1 also. You calculate the Q2, Q3, Q4, everything, the outflow for the intermediate point. Let us call that as Q dash 1, Q dash 2, and everything. Then you use these as the inflow for the second reach and then calculate the final Q1, Q2, Q3. Right? So this is the approach to do that. But I don't feel that in the gate examination you are going to get these kind of questions. But you remember that C1, C2, C3 can be negative. But when they are negative, we have to go through a longer procedure to get to the answer. So I hope you got something new from this discussion. But the answer to this question was very simple, that what is the sum of these coefficients? Sum is always going to be 1. If some value is negative, the other value is going to be higher. You have to keep that in mind. Okay, let's go to the next question. Before we go to the next question, let me just for my sake, let us take one more question related to the Muskingum method that actually is very basic, but often we see that we are having difficulty answering that question. So I'm going to answer this question because this is a recording, but I would want you guys to pause the video and try to answer this question. So the question is, we use the Muskingum method for routing which of the following? Option A, hydraulic. channel. Option B, hydrologic channel. Option C, hydraulic reservoir. Option D, hydrologic reservoir. So now is the time to pause the video and look at these options and let me know what is the answer. Alright, so I hope you guys gave the answer as hydrologic channel because that is the correct answer. Now, what is the difference between hydraulics and hydrology? Hydrology is the field where we try to get the outflow at the catchment or at a watershed based on the rainfall, precipitation, infiltration, and counting all these things. So that is what basically we try to do in hydrology. In hydraulics, we try to see how the fluid is flowing. What are the reasons for the fluid to flow? What are the forces that are affecting the fluid flow? So here we try to study the fluid flow, all the forces, all the frictions and everything related to that. But here we are not concerned with it. Here we are just all the calculation that we are doing in hydrology is to get the outflow from a catchment, from a channel, or from a reservoir. We are not in very much interested in how the flow is actually occurring, right? So in case of Muskingum method, we are basically doing the routing for hydrologic channel. One more thing, one more takeaway from this thing, for Muskingum method is this storage term that we saw this equation S is equal to kxi plus 1 minus xq. Here, when x is equal to 0, then the storage becomes solely the function of the outflow, and that we call as a reservoir routing. All right, just a one-liner question that can be asked. A very simple one like that. Okay, let's go to the next question. GATE 2010, question number 18. I apologize for this bad quality of the text, but I could not get a good text from the PDF, and I think it is readable. So anyhow, I'm going to dictate it so you can, if you are not able to read, you can uh, listen to what I say and you can make out what is written there. The correct match of group 1 with group 2 is, so group 1 is a set of variables and group 2 is a set of methods or equations which you are going to use. First one, evapotranspiration, in second, infiltration, then synthetic unit hydrograph and channel routing. Now in group 2 we have the methods. First one, Penman method, second, Snyder's method, Muskingum method and Horton method. So let us see what are the methods. Evapotranspiration. So we know evapotranspiration can be measured using our aerodynamic method, using our energy balance method, but most accurately throughout the diurnal day we saw a combined method, right? That combined method, when modified, was also known as Penman-Monteith method or simply as Penman method for evapotranspiration. So P is related to 1. Now infiltration, we have Green-Amp method, we have phi-index method, and we have Horton's method. What was the equation for Horton's method? It was Fc plus F0 minus Fc e power minus kT. So infiltration rate at any time potential infiltration rate, you have to remember to call it as potential infiltration rate at any time, was given as the constant infiltration rate after infinity plus initial infiltration rate minus the constant into exponential minus kt, where k is the decay constant for the exponential drop in the infiltration rate. So this was the Horton's method, right? So we have the coupling for Q as 4. Okay, now synthetic unit hydrograph. Why do we need synthetic unit hydrograph? In many cases where we have the unit hydrograph, how do we measure it? We have a flow meter at the outlet of this watershed, and then we have various, rain gauge stations inside the watershed to get the precipitation in the watershed, what is the depth of the precipitation, and then what is the flow rate. So basically we are able to get what is the rainfall axis and the unit hydrograph. But there are a lot of catchments in India and in many places where it is not feasible to provide maintenance to these equipments, that we don't usually get the all these data for these catchments. So what do? We find out a catchment which looks much similar to these catchments, which has a topographical property and soil property similar to these catchments, and then we try to get a synthetic, we try to manufacture a unit hydrograph for this catchment based on the catchment that we already have. So that is the use of the synthetic unit hydrographs. So what is this Snyder's method? We are not going into the detail, but Snyder methods uses some parameters of this unit hydrographs to construct a synthetic unit hydrograph. So if you have a unit hydrograph like this, let's say this is the excess precipitation, PR is the duration of the excess precipitation, and this is your rainfall hydrograph. So then we use some of the variables. First one, let's say we call it as peak discharge, QP, peak discharge. Second one, let's say base time. So TB, base time. And third one, we have lag time. Lag time. So we use these three parameters to actually get the uh, synthetic unit hydrograph. So the peak discharge and the base time are pretty evident from their name itself, but the lag time is often confused when we try to define it. So the lag time is defined as the time from the centroid of the excess precipitation to the peak of the unit hydrograph. Okay, so it's not the center of the excess precipitation, it's from the centroid of the excess precipitation. All right, so we know that the matching for R, that is the synthetic unit hydrograph, is going to be Snyder's method. So what is left? We have already seen this one. Channel routing is going to be Muskingum method. So do we have 1, 4, 2, 3? So we have 1, 4, 2, 3 in option number B. So that is the correct answer. All right, let's go to the next and last question for this week 19 session. So question is from GATE 2007, question number 56. An isolated 4-hour storm occurred over a catchment as follows. Time is given. For the first hour, precipitation was 9 mm, second hour 28 mm, third hour 12 mm, fourth hour 7 mm. The phi index for the catchment is given as 10 mm per hour. The estimated runoff depth from the catchment due to the above term is how much? So let's draw the hydrograph for the precipitation that is given to this question. So we have from 0 to 1 hour, we have a precipitation of 9 mm. So let's say this is 9. Then for second hour, we have 28 mm precipitation. So it's going to be a very big bar. Then third hour, we have again less precipitation, 12 mm. And fourth hour, we have the smallest precipitation, that is 7 mm. So this is the time in hour, and this is the precipitation, total precipitation in mm. 28, 9, 12 and 7. And interestingly, we are given the phi index value as 10. So when we draw this phi index, this is going to be 10 mm per hour. One thing to note here, see, gate is becoming tricky these days, and this is a very old question. So they have not used much trick in this question. But nowadays, what they are trying to do, see, they are going to give you this precipitation instead of 1 hour. For 1 hour, they might give you the precipitation for like 2 hours. And instead of this 4 hour precipitation, they may say that okay, it was a 4 hour storm, but the precipitation are given in 2 hour interval. And if you don't read that carefully, you are going to use this given phi for 1 hour, that is the 10 mm per hour, and just simply subtract and get the wrong answer. But in that case, you have to also convert your phi from per hour to per 2 hour. Right? In this question, we don't have to worry about it, but nowadays GATE is introducing these kind of tricky questions, and you have to be aware of these things. Okay, so now to solve this question, we need to know how do we calculate the phi index. Phi index is given as precipitation which uh, when the intensity of precipitation was greater than the infiltration index or the phi index minus the runoff divided by the time where the precipitation was more than the phi index. So basically what we do, we assume a phi index. When we calculate this phi index, we assume a value of phi index and then calculate this PE minus R divided by TE, and then check whether the phi index that we have gotten satisfies the criteria of all these precipitation events being greater than the assumed phi. If that is correct, then your new phi is correct. If your new phi is somehow creating an issue with it is coming more than certain precipitations that you have assumed, or if it is coming less than certain precipitations, then you have to use that phi, the new calculated phi, and then reiterate to calculate the second phi. So if you know this, how do we calculate phi, this question becomes very easy. So let's see, in this question, we are already given the value of phi. So we'll just write here all these value of the parameters. So we have 10 mm per hour for phi. Now PE, what do we have to write here? We have to write the total precipitation when the precipitation or intensity of the precipitation for certain hours was greater than 5. So we'll have 28 and 12, right? Because 9 and 7 are less than 10, so we are not going to count them. Then subtract R, the runoff, and then TE. TE is also the total time where the precipitation intensity was greater than 5. So it is also going to be 2. So we can easily solve this question. We have here 40 minus R. So 2 can go here and become 20. So R becomes 20 mm. So the runoff depth was 20 mm. So let me just highlight this. So according to the phi index, only this much rainfall contributed to the runoff because the other rainfall was, sorry, less than the fine index or the infiltration rate, and it ended up in going inside the soil rather than contributing to the runoff. So I hope this question was, you were able to understand this question and get the right answer. All right, so that's all for this session. Thank you and have a nice day.